Okay, let's start. Topic 4, materials, chapter 4.2, solid materials and properties. Under this, we will learn about Hooke's law, Young modulus, and some other topics like energy in springs and so on. Okay, so let's start with Hooke's law. You have to know the definition of Hooke's law. By the end of this section, you should be able to understand Hooke's law and be able to make calculations using it. So we will have some equations, F equals kx and so on, and then calculate the elastic strain energy stored in a deformed material. And this is also called the work done on the deformed material. In our case, it would be a spring. Okay, so the elastic strain energy of a spring is also equal to the work done on the spring in stretching or compressing that spring. Okay, so when you have a normal spring which is at its original length, which is neither compressed nor stretched, and if you stretch it, what will happen is the spring gains elastic strain energy, and to have that, for the spring to get that elastic strain energy, you have to do some work in stretching or compressing it. Okay, so that's why we say the work done on the spring is equal to the elastic strain energy of the spring. Estimate the elastic strain energy stored from a force extension graph for a sample. And also from a graph, the area under a force extension graph is the elastic strain energy or work done on the spring or other material. Okay, so let's say we have here tension and extension, and then we have compression. Now here the first one is where we have tension. Okay, so we are pulling this bar or spring from both sides. We are applying what we call a tensile force. So if we pull an object from both sides, then we are applying a tensile force, and this causes it to extend. Whereas if we apply a compressive force, okay, maybe we are pushing it down, okay, maybe squeezing it, compressing it, that will cause the length to decrease. And here we have a compressive force, and that gives a negative extension. Actually, it's a compression. So for we use the word interchangeably. Okay? At times we say, even for the compression, we say, at times we say extension. Now, if you are using F is equal to Kx, that's why I said, so if you use this equation F equals Kx, this can also mean compression or negative extension. Okay, so if you consider a spring in the suspension system of a car, that spring gets compressed, but the springs we have in the physics lab, they can be extended. Now, normally a spring like this you can't compress, but it can be extended. But if you look at the springs in the shock absorber system of your car, those springs can be compressed. Okay, so we have Hooke's law is best described mathematically with this equation. The applied force is equal to the stiffness constant times the extension. The stiffness constant, K, is also called the stiffness, elastic constant, spring constant. All those words are used to mean the same thing. Okay, see, the stiffness constant for a spring is usually referred to as the spring constant. Either phrase refers to K in the Hooke's law equation, and you should know what Hooke's law is. Okay, this is what we have. This is the equation. A material only obeys Hooke's law if it has not passed what is called the limit of, okay, so this is not the Hooke's law. This material obeys Hooke's law up to what we call the limit of proportionality. Yeah, here is Hooke's law. Hooke's law states that the force needed to extend a spring is proportional to the extension of the spring. And you have to know this definition. Okay, maybe later on at the end of the chapter also, I think they have the definitions. Limit of proportional extent compression. Okay, anyway, you have to know the definition of Hooke's law. Okay, and it is given here, and this is the equation. And Hooke's law is obeyed only up to the limit of proportionality, because if you draw a graph of force versus extension, it will be a straight line only up to a certain point where the spring or the material is not stretched beyond its elastic limit. Okay, so here let's say we have the applied force F here, and or the force in the spring rather, and this is the extension. Okay, so it applied force. Normally the independent variable is on the x-axis, the dependent variable is on the y-axis. So let's say this is the applied force. So then this is the independent variable because the applied force produces the extension. The extension X depends on the applied force. Okay, but if it was the force in the spring, then we have to switch the axis because greater the extension, greater the force in the spring. All right, let's have a look at this. Okay, so we will get a straight line up to a certain point only. That point is called the limit of proportionality. Now, I will call it L, limit of proportionality. Now, once this is exceeded, what happens is the curve will no longer be a straight line. Okay, so it will try to curve that way, meaning for a small force you get a little bit larger extension. So the graph will curve in that direction. And here somewhere here we can have the elastic limit just after the limit of proportionality. In some textbooks, the limit of proportionality is at the same place as the elastic limit, but limit of proportionality always comes before the elastic limit, or elastic limit and limit of proportionality at the same place. You don't have the elastic limit before the limit of proportionality. Okay, and we have, let's say this is called the elastic limit. Okay, so what is elastic limit? A material returns to its original shape when the deforming force is removed if the material has not exceeded the elastic limit. If the material exceeds the elastic limit, then once the deforming force is removed, it will not return to its original shape. Okay, so now here we have something like this. Okay, so let's say a force is applied so that the material is extended beyond its elastic limit. Then what will happen is once you remove the deforming force, the material will not return to its original shape. Now say this can happen with a spring also. Now if you stretch a spring too much, what will happen is once you remove the deforming force or the extending force, the spring will not have its original length because it has been deformed, permanently deformed. Okay, so permanently deformed. An object will get permanently deformed when it's stretched beyond its elastic limit. Okay, so we have this one. Now in some books you might see it the other way. So this is, I will call it A, applied force. Okay, the extension in the spring depends on the applied force. And let's say we have here.
So in the end, sir, why it is curving upwards?
Because once it is stretched beyond this point, even for a small force, it will extend a lot.
So no, so after the elastic limit.
Yeah, it still continues to stretch. So it is permanently deformed. Do you get it? The length of the spring, once you stretch it beyond its elastic limit, will be longer. The spring will not regain its original shape if you stretch it beyond its elastic limit. Now let's say here this is the force in the spring, Fs I will call it. Okay, so the greater the extension, greater the force in the spring. Again, this will be a straight line, but this will curve this way because here we have the extension. Okay, let's say this is in millimeters. Here, let's say the force is in newtons. Always it curves to the extension side. Now in this case, it will curve to that side. In this case, it will curve to this side. And by the way, the area between the curve and the extension axis, okay, let's say this one. This is the work done on the spring. Also, we can say now the work done on the spring is the elastic strain energy of the spring, of the material. It doesn't need to be a spring. Okay, so same way here. Now here it will be this area. There was a past paper question where they had asked, they have not really shown much detail, and they had asked which area it is. Now remember, first thing when you get a graph is to see what the axes are. So if the extension is on this axis, then it will be this area because it is always the area between the curve and the extension axis that will give the work done on the spring. So again, this is the work done on the spring. The work done on the spring is equal to the increase in elastic potential energy of the spring. So we can also say the work done on the spring is the elastic potential energy of the spring. And you can see up to the limit of proportionality, the extension or the extension is proportional to the applied force. Okay, or we can also say here up to this. Okay, so where it begins to curve is where you have the limit of proportionality. So in this case, the L will be here. Okay, so we have again we can write the applied force is proportional to the, not applied force, the force in the spring is proportional to the spring's extension. Okay, so if you rearrange this and if you work this out, how you convert a constant proportion to an equation is by adding a constant. So here we have a proportion, here we have an equation. So this will be the spring constant or the elastic constant or stiffness constant. There are different names to mean the same thing. It's also called stiffness. Okay, so you have to understand what is limit of proportionality, what is elastic limit. You have to know this equation. Now this X can be compression or extension. If it's compression, then this will be the compressive force. If it's extension, then it will be a tensile force. F will be a tensile force. Okay, here is an example. A spring has a stiffness of 50 newtons per meter. Now you can see, you can figure out the unit of K by the unit of F and the unit of X. This is in newtons, this is in meters, so K will be in newtons per meter. A spring has a stiffness constant of 50 newtons per meter and is 3 centimeters long naturally. How long would it be if a 200-gram mass were hung from it? So the K is given and the original length is given. Now remember, extension is final length minus the original length. Extension, this X here is the extension. Okay, so extension we can say is equal to the final length minus the original length, or instead of writing X I could have used L. That's better, I guess, because X is the standard, the letter we use for extension. So final length minus the original length is the extension. Okay, K is given, initial length is given, the original length is given, and they ask how long would it be, that is the final length. You see, they're asking the final length. How long would it be if the 200-gram mass were hung from it? So we can first find the force. Now, once a 200-gram mass is hung, that will be the force in the spring. Okay, the weight is equal to the force because the spring gets extended and it stays there. So the downward force on the spring will be equal to the force, upward force in the spring. Say you have a spring, and if something is added here, then the weight of this should be equal to the force in the spring, because the two forces are balanced, it's stationary. Okay, this is stationary, U equals 0, meaning it will be in equilibrium. So the upward forces should balance the downward forces, and that's what they do in this example here. They first find the weight of the object that is hung, which is this one, and you can see they make that equal to delta F, because that is also equal to the size of the force in the spring. And this delta X is the extension. Now K is given, so we make delta X the subject of the equation. K is 50, all are in SI units, so we get our answer also here in SI units. Then we can convert it to centimeters. Now they have not asked us the extension, they have asked us the final length. So final length is what? Original length plus extension. I wrote down the equation here. The extension is final length minus the original length. Therefore, the final length will be extension plus the original length, which is this. Then okay, so that is about that. And you can see here the gradient of, now this is, okay, by the way, I can also tell you about the gradient of the graph. Now if we have a graph like this, okay, so we have f equals kx, then the y value, so this is a graph of y equals mx, y equals mx plus c, but the plus c part is 0 because it's passing through the origin. This is the origin, it's passing through the origin, so the y-intercept is 0. This is the one here, it's the force, and then the x is the extension. So what is on the x-axis is the extension. Then on the gradient will be the stiffness constant or elastic constant. Do you understand? So if you calculate the gradient of this, let's say the gradient is m, that is equal to k. Over here, it is equal to 1 over k, because this is the reciprocal of the gradient, that is equal to k. So here we can say k is equal to 1 over the gradient. M is the gradient. Okay. So now this is the equation, this is the proportionality. So if you write this as f equals kx, you can see that k is 1 over m. Okay. If you want, I can also show you that. So here we have again the same equation. F is equal to kx. I'll write it here. F is equal to kx. But we'll have to rearrange this because x is on the y-axis. So x is equal to 1 over k times f. Can you see that I moved this to the other side? Then this is my y, because here this is on the y-axis. Then you can see, if you see this will be your y, the x will be your y on the y-axis rather. What is on the y-axis is this, and this is the y equals, so sorry, y equals mx, right? So here this whole thing will be your y gradient, okay. And then this is on what you have on your x-axis, which is this one, okay, fa. Any questions?
No, sir.
Okay, then the other thing you have to know is the area. Now I told you this thing about the area earlier. The area under the force extension graph is the work done on the spring or the elastic strain energy, elastic potential energy in the material or in the spring. So this is a what? This is a rectangle. So the area which is equal to the work done is equal to the area of a triangle, which is half into, this is the base. Okay, so let's call it x into f, base into height, half into base into height. So if you have a graph like this, the work done on the spring or the elastic strain energy in the material is equal to half fx. I just rearranged the equation. Can you see I switch these two? So you should know this equation. Got it?
Yes.
And you should know which area. Okay. Now if it was the other area, if it was this, then it will be this area. Still you have the same formula. Okay. And also you can use this formula up to the elastic limit. But if you want beyond this, then you may have to use some other equation, or you may have to estimate and find it. But even here, even if you consider this area here, that is also the work done by the spring. So on the spring or elastic. So it's the whole area. Now, if it is extended all the way up to here, then the work done will be the area of this whole thing. Work done on the spring or elastic strain energy in the spring will be this whole thing. Is that clear?
Yes, sir.
Okay, now for f, you know, f is equal to kx. So we can also write this as half. Okay, so the half is there. Then f is what? Kx. So half k times x, kx squared. Got it? So
Yes.
another formula for work done on a spring or elastic strain energy in a spring is this, half kx squared.
So I x squared, sir.
Because f is equal to kx, you see. So I
Yeah.
substituted for f there.
Okay.
Then I get kx times x, which is kx squared.
Okay.
Okay. And if you make x the subject of this equation and substitute there, then what you will get into this? So we have half then. So x the subject means f squared over 2k. You see that?
Yeah.
Make x the subject, substitute in there for x, f squared. But this is these two are the two main equations you will be using. Okay, they will give you the graph, so you have to find the area of the graph, and that you can find using this equation up to the limit of proportion. If you want to find beyond that, you will have to do an approximation or calculate the area, maybe using estimation, something like that. Okay, so here is an experiment to show that. Okay, so they increase the weight and then the length, original length, loaded length, that is the final length, the extension, and then they draw the graph. Okay, then the gradient is k. Can you see here? Because this is f versus x, like what I have here. Okay, f versus x, then the gradient will be k. Okay, then we have this half Fx. Okay, so you see half Fx, that equation, the elastic potential energy in the spring. So half Fx, that is this one. Okay. And you can also calculate the area to give the, so that's what they're doing here. So they find, now you can see this is F versus X. So it is between the line or the curve and the X-axis. Okay, between the curve or the X-axis. So then we have this area. And you can find the shape separately, the area of the trapezium plus the area of the rectangle.
So why are you not finding the whole thing, sir?
Yeah, we are finding the whole thing. See, that's what they are doing here. This is figure D. They're talking about figure D. What is the elastic strain energy stored in the material shown in figure D if it is extended by 12 centimeters. Now, you can use this equation if it is a straight line only. But here what do we have? Straight line, this thing. Because if it's a straight line, then that is a triangle. These two equations, these three equations can be used if the shape is a triangle. But beyond that, what do we have now? We don't have a triangle after this 0.04. So therefore, we can't use this equation to calculate this full area. Only up to this area we can use it. Find the total work done on the spring or total elastic potential energy stored in the spring when it is extended to 0.12, then we have to find this area. So we can consider this part as a trapezium, this part here as a trapezium, and we can use formula for trapezium, and also here, this part is also a trapezium. So that's what they are doing. Okay, they are finding the area of the trapeziums, and that will give you the energy stored in the material when it is extended by 12 centimeters. Triangle from origin, area, and this, yeah, you can also find triangle. So first, but the easiest way is to use two trapeziums because then less work. So if you want, you can find the area of this triangle, then this rectangle, that's what they are doing, triangle, rectangle, and then the last part they use a trapezium. Okay, this one is the trapezium they are using. Or else, like I said, you see this figure here, that is also trapezium. You have two parallel sides, this side and this side. And in this case, this is trapezium. The vertical lines sides are the parallel sides. This side and this side are the two parallel sides. Okay, so that's the end of that part. There are some questions. Make sure you do all of this. Make sure you do all the questions, and these definitions are important. Okay, they tell you what is tension, extension, compression, limit of proportionality, elastic limit, spring.
Graphs there above it.
This is a question.
Yes, a graph.
So here you have force, you have extension. The area under this is the work done. So here, yes. I think this is for a rubber band. Yes. So initially the rubber band is loaded. Can you see the blue dots? This is when the rubber band is loading, the top line, the top curve. So when the rubber band is getting loaded, that you have that. When it is unloading, the rubber band follows this path. So it doesn't obey Hooke's law, because if it obeys Hooke's law, then it should be a straight line passing through the origin. But here it's a passing through the origin, but it's not a straight line. So this rubber band doesn't obey Hooke's law, because it's not a straight line for force versus extension graph. So what happens is, now in the beginning the weights are added and the rubber band extends. Okay, so up to here weights are added. Now the area under this blue curve will give you the elastic strain energy in the spring, or elastic potential energy in the spring, or work done on the spring. Now what happens is, when you remove the weights, the extension becomes less and less, and then it comes back here. So it followed a different path. Okay, so when you take off the weights, what happens is the work done or the elastic strain energy in the spring keeps on decreasing, because it is extended, it gets less and less extended, meaning the extension is less. Okay, so when you remove weights, the extension is less. So if the extension is less, the elastic strain energy in the rubber band is less. Okay, so up to this point. Now the area here is the energy dissipated. That is the energy lost as heat. If you find the area of this under the blue curve and the area under the green curve, and if you subtract that, you will get the energy dissipated, or energy that was converted to thermal energy. Okay, and like I said, this is very important. Okay, for the extension of a material sample, hysteresis is where the extension under a certain load will be different depending on its history of past loads and extension. So you have that here. Okay, different extension during loading and unloading is an example of hysteresis. Okay, so make sure you go through this, do all the questions, and if there are any problems, just let me know. Any questions?
No, sir.